Hi everyone, thank you for tuning in. My name is Nicholas and I'm a PhD candidate from the University of Michigan. And today it's my pleasure to share some research on the Titus Canyon Formation in Death Valley, California. So our region of interest is the Basin and Range Extensional Province of Western North America, which, since it's one of the best exposed and most easily accessible areas of continental extension in the world, has attracted an enormous amount of research over the past decades, which has created a lot of data that constrain the tectonic and topographic history as this region has evolved and extended. And this compilation of data has enabled us to build recently beautiful models, such as this model from Bahadori et al. 2018, which takes in measurements of upper crustal strain compiled in McQuarrie and Wernicke 2005 and inverts them for the evolution of crustal thickness and topography, assuming those upper crustal strain measurements through time. And the challenge with models like these are that they inherently are unable to take into account geodynamic mechanisms like lower crustal flow and magmatic addition, which, while we know we're likely operating during extension, wouldn't have left an upper crustal strain signature and therefore couldn't be incorporated into a model like this. And so an important test for models like these is to compare their predictions to independent measures of topography. And a great way to measure topography, especially 36 million years ago, before extension acted on the region, is to look at hinterland sedimentary basins that were deposited up on that high topography. Hinterland strata are windows to the initial conditions of the basin range before extension acted upon it. And on this map, I've highlighted a number of the more famous hinterland deposits: the Elko Formation in the north, the Sheep Pass Formation, and the less studied White Sage Formation. And the challenge with hinterland basins is that we are limited by their temporal and spatial extent. And moving south into the central basin of range, we haven't seen a similar depth of research into hinterland deposits because the oldest Cenozoic rocks in the central basin of range, directly above the subtertiary unconformity, are notoriously difficult to date due to a lack of tuffs as well as significant lateral variability, making correlation more difficult. And this results in a lack of strong geochronologic framework and stratigraphic framework onto which you can build more intensive studies, isotope studies and things into the hinterland deposits. And so today I want to introduce you to the Titus Canyon Formation, which is an understudied hinterland deposit from the Central Basin Range in Death Valley that we did some work on to establish some of that geochronologic and stratigraphic framework that can hopefully serve as a platform for building more future studies. So taking a look, here's a view north from the Central Basin Range here, the Northern Basin Range in the background. This is Death Valley, and I've highlighted the ranges around Death Valley. Our study area is in northern Death Valley, and it's going to focus on the Grapevine Mountains and the Funeral Mountains. So the next image is looking from the Funeral Mountains northwest along the Funerals and Grapevines, and we're going to take a look at the structure of the region. So in this image, I've highlighted the outcrop extent of the Titus Canyon Formation in green, and in yellow and red, we have the two major detachment faults that are structurally important in these ranges. So the major one is the Boundary Canyon Detachment Fault, which separates metamorphic rocks in the Funeral Mountains from the unmetamorphosed myogeoclinal Paleozoic and Neoproterozoic rocks in the Grapevine Mountains in the hanging wall. And the Titus Canyon Fault is a smaller detachment fault, older than the Boundary Canyon Fault based on cross-cutting relationships, and probably produced some of the basin accommodation that the Titus Canyon Formation was deposited into. And so a very brief history of the Titus Canyon Formation itself. Stock and Bode in 1935 were two paleontologists who were excavating an assemblage of mammalian fossils from the Titus Canyon Formation, including a Titanothere skull here shown on the left. And they did the early preliminary stratigraphic work. And here's some photos of Stock and Bode working in the 1930s. we have collaborated with some paleontologists, and we're actually relocating some of the paleontological sites from Stock and Bode from the 1930s, and so we matched those images to their modern outcrops. 30 years after Stock and Bode, Reynolds in 1969 did a PhD thesis in the Grapevine Mountains, mapping the stratigraphy and expanding the mapped extent of the Titus Canyon Formation. And finally, a renewed interest in the 90s and early 2000s from a number of master's theses and PhD theses finally added a handful of argon-argon ages, importantly, although those were not very well correlated into the rest of the exposures of the Titus Canyon Formation, because a lot of that stratigraphic work still needed to be done. And so some outstanding questions still after this body of work remained: improving the internal stratigraphy and correlations of the formation, and a better geochronologic framework for the formation. And so to do that, we went on 2 field seasons in 2019 and measured these sections and produced this map. And for the purposes of this presentation, I'm just going to show the simplified stratigraphic column, which is a composite of all of our stratigraphy that we measured. So I'll begin just with a brief summary of the lithostratigraphy of the formation. So we divided the formation into 2 members, a lower red bed member and an upper variegated member. The red bed member is purplish gray class supported fanglomerates near its base, very coarse, fining generally upwards into cross-bedded pebbly sandstone channel deposits with brick red overbank deposits. Here you can see that fining sequence in image A, going from the left here, where it's dominantly coarse conglomerates, and then moving up section to the right, you can see they give way to these fine red overbank deposits. And importantly, the red bed member had no tuffs that we could find, which makes it challenging for radiometric dating, of course. The variegated member is very distinct and has a really different lithologic character than the red bed member. It has a different sediment color overall. It's much more yellow and green, and it has limestones included in it, in addition to cross-bedded conglomerates and these brick red silty overbank deposits. The variegated member did include a number of tuffs, a few tuffs that we were able to extract ages from. And so we'll look at that geochronology now. So here I've listed out the detrital zircon spectra from the samples we took from the stratigraphy. And we decided to use detrital zircon maximum depositional age constraints because of how poor even the best tuffs that we found looked. They were all reworked tuffs. And we had success in the variegated member. We were able to pull out these young populations of zircons that gave good maximum depositional ages. I also mentioned earlier the argon-argon ages, which had been previously analyzed. We compiled those from a variety of sources, published and unpublished, and placed them within our new stratigraphic framework. And they largely agree with our MDAs, giving the variegated member an age span of about 35, 34 MA to 30 MA. Now, the red bed member we weren't able to get any radiometric dates from, but we were able to relocate those fossil localities from the 1930s into the upper red bed member, giving that interval a Duchenian age based on that fossil assemblage. And so between the biostratigraphy and our new geochronology, we have a relatively good age structure for the whole formation, ranging from around 40 MA to 30 MA. So finally, I'm going to zoom out on those detrital zircon spectra and show the full spectra, where we were able to get actually a quite interesting provenance signal from the formation. And I've summarized the age peaks here in these bar graphs. And so on the left are Cenozoic grains, in the middle are green Mesozoic age grains, and then on the right are Paleozoic and older grains. And these sources represent fresh volcanic input into the basin, the Cenozoic input. The Mesozoic peaks are most likely coming from the Sierra Nevada Arc to the west of the basin. And the recycled older broad spectrum ages are representative of the local bedrock of the central basin range, which is the Cambrian and Neoproterozoic myogeoclinal rocks. And what we observe is that across the red bed to variegated member transition, we see the signal change from almost exclusively Sierran Mesozoic provenance to a primarily Paleozoic provenance, along with the addition of those fresh volcanic zircons. And we believe that that change from a Sierran source, which a Sierran source would be very rich in zircons, to a recycled Paleozoic myogeoclinal source, which would have been very low in concentration of zircons. Those the myogeocline is primarily shales and limestones. Really signals that there must have been a dramatic shift in the catchment geometry of the basin. And so this gets, putting all of this together, this takes us to a question of climate and tectonics. What happened across this red bed to variegated transition around 35 to 34 MA? And of course, that aligns really well with the Eocene-Oligocene glaciation event at 34 MA. And so we can't exclude the potential influence of a really dramatic climate change at this interval. And so some characteristics of the basin that we see change across the red bed to variegated members are easily explainable through a climate change, like color change in the sediment, oxidation state, appearance of lacustrine limestones, maybe signaling a change in the hydrologic conditions of the basin. But we do believe other aspects are more likely a tectonic effect, including the appearance of those tuffs and the increase in fresh volcanic input, maybe signaling the encroachment of the ignimbrite flare-up as the delaminating Farallon slab comes closer to the basin. And also that change in provenance, we think that has to be a signal of basin reorganization, catchment reorganization. And so placing this basin, now that we have a better framework for its age and its stratigraphy, into the context of these other hinterland basins I mentioned at the beginning, this figure shows three main pieces of information. In blue, we see the isochrons of the Farallon slab as it delaminates, sweeping from north to south. And in orange, we see the hinterland basins, and the numbers are the approximate timing of their depositional ages. And in black are metamorphic core complexes, which I've put on the ages of their initial exhumations. There's been hypothesized a kind of pattern of paired hinterland deposition in a basin, followed by nearby exhumation of a metamorphic core complex. And the Titus Canyon Basin fits well with this. It shows deposition before the Farallon slab's arrival, ending around when the Farallon slab arrives, delaminates in the Central Basin Range, and then followed by the rapid exhumation of the Funeral Mountains core complex along that boundary canyon detachment fault. And so the Titus Canyon Basin, I think, fits well in a tectonostratigraphic context with these other basins and may be an ideal place to further extend our isotope studies and paleotopographic studies from these basins into the Central Basin and Range. As a final note, here I've overlain a number of relevant geologic pieces of information onto the topography, the 36 MA reconstructed topography of Bahadori and Holt 2019. Who had that beautiful animation I showed in my introduction. And I want to highlight a discrepancy between their inferred topography, which is primarily informed by the location of these metamorphic core complexes, and therefore this record of extreme upper crustal strain, and the fact that we have hinterland deposition happening generally west of those core complexes, between that inferred topographic crest along them and some hydrologic divides that are inferred by Henry and Best along central Nevada. The discrepancy between the inferred topography from Bahadori and Holt's model and the hinterland strata and divides, which maybe outline a Nevada plano or high orogenic plateau that occupied this region, highlights the need for us to consider other geodynamics like lower crustal flow and magmatic addition, which together may act as a buffer for the upper crustal strain record and explain some of these differences we're seeing between the modeled topography and data. And finally, I'll leave you with these conclusions. The Titus Canyon Formation, we believe, spans approximately 40 to 30 MA across the Eocene-Oligocene boundary, and it might be the oldest Cenozoic hinterland deposit in the Central Basin and Range. The Titus Canyon Formation matches the patterns shown by hinterland deposits farther north, and also might be one of the southernmost basins deposited on the hypothesized Nevada plano. And so with that, I'll thank my funders, the USGS and GSA, and thank you to our collaborators as well.